who joined me the workshop today. My name is Manuela Campanelli. I'm one of the organizers of the workshop and the PI of the Theory and Computational Network on Binary Neutron Stars Astrophysics. And so I welcome all of you, and I wanted to remind some few important aspects concerning the information related to this workshop, and then we can start with the talks. The chair of the workshop this morning is Josef Zlochower. So it will be making sure that the talks are ending in time and taking the time for you for the questions. So, okay, let me start with some information, key information here. And if you have any question, please, raise your hand and or speak up if I don't see you, with your hand raised. So here's the information concerning the schedule, which is posted by now. You should have seen it. This is the program for this morning. I will present briefly, give you an overview of the project, which is at the base of why we're doing these workshops every year. And then we're going to have Masaru Shibata to give us an overview in the field, and Jacob Lunch later on observations related to the LIGO observation and telling us the news that we all are grateful to have these days. And then after there's going to be a brief break, and we are going to hear about simulations using Illinois GRMHD with Leo Wernick, and simulations with Spritz by Lorenzo Energy. And finally, we're going to have a break, and we're going to have an afternoon session chaired by Neil Sanderson from University of Southampton and Cole Miller from University of Maryland. I just remind you that these are more than chairs, they are actually discussion leaders. So they will be driving the discussions. And I'm sure that they already pulled out a series of questions and interesting topics to discuss for the afternoon. So I expect this to be a very lively, interacting environment. Please come in, even if it does not appear yet to be structured. There will be some slides, and there will be an organization by the chairs that we're gonna see as soon as you're coming in this afternoon. So, okay, so this is a summary of the information for the workshop. You also have a Slack channel where you can conversate, and there are on each on the channel you're going to see different, actually a Slack space, you're going to see different Slack channels there for each day, where we can use these days to discuss the various topics related to the talks, as well as the discussions in the afternoon. There is also a social media team this year. This is new. We didn't have it last year. I think this year we're lucky to have young people in the team that can do this. So if you're interested in having your talk publicized, actually it will be publicized, and please use the hashtags that have been circulated on Slack. But we are going to publicize the talks over Twitter, Facebook, and there is a YouTube channel where the recording will be posted. Okay, so there is a Google Doc link as well, and the chairs before we end the day today, I will want to hear a little bit about the chairs about pointing us in the direction we're going to go in the afternoon. But there is a document here where some of the discussions are already happening. Okay, so then I want to first of all mention the names of the people who have been behind the organization of this workshop, both on the scientific organizing committee and a local organizing committee. So you can see them here. Especially if you need anything from the team, the local organizing committee team. So you see their names here and their associated roles in helping organizing this workshop. Okay, and finally, I want to take a moment to read our diversity and inclusion statement. Please take all few minutes, but I'm going to read it for you. So I'm making sure that this is actually conveyed. So we're committed to creating a respectful and inclusive community environment that invites participation from everyone, regardless of gender, sexual orientation, disability, physical appearance, body size, race, nationality, or religion. Our community is based on mutual respect, tolerance, and encouragement. And we're working to help each other live up to this principle. We want our community to be more diverse, wherever you are and whatever your background, we welcome you. Additionally, we aim to always be respectful to our environment and strive to be environmental friendly in all our events. Okay, so having said so, if there are no questions about the organization, I would like to go over my talk. Okay, so I do not see any hand raised. I'm sure that if there is a need, people will contact me. So I'll go on to my talk right now. Okay, so I will be giving you an overview of the TCAN projects, which stands, TCAN is a program at NASA, which stands for Theory and Computational Astrophysics Network. And our group with other 3 institutions and collaborating institution was awarded such a project about now almost 3 years ago. And our intention was to, as the title suggests, to build a set of advanced computational tools to study the dynamics of ejection accretions, winds and jets in neutron star mergers, but not just in neutron star mergers, also black hole neutron stars mergers, but with prevalence to neutron star mergers. Okay, so as I said, we have 4 PI institutions, RIT, Johns Hopkins University, Goddard Space Flight Centers at NASA, West Virginia University now moving at HIDO, and multiple international collaborators spread over several institutions. So I hoped I'm inclusive, but I might have forgotten someone here because the team has been increasing, and that's really nice. But you can see their international nature. And in fact, we have about I think 43 us today participants in this TCAN. And we are structured around working groups. We are coordinated all together, obviously. We meet weekly and we do connect with the external community formally through this workshop every year. So we are also aimed at building these software tools so we can release a large part of them to the community and build a community through this compact binary resource that we have online. So you might check it out, it's compactbinary.org. Okay, so again, so this is thanking to support majorly to NASA through the TCAN, but also other satellite NSF grants, and of course, resources that we have in the TAC supercomputer system for computation. Okay, so we started with the goal, obviously, to understand what happens in binary neutron star mergers, and obviously the observations have been the driving force started by the gravitational wave observations, that the multi-messenger observations that were associated with the first binary neutron star merger was our motivation to start this TCAN. Things have changed quite a bit, and Jacob Balanche will review a little bit about the status of the observations concerning binary neutron stars and black hole neutron stars today. So I'm not going to say much today, except that this is really an exciting time to work on this topic. Okay, so what really was our goal? Our goal is the goal, I guess, that everyone has to perform long, accurate simulation in full 3D, obviously including all the physics that is required to model this complex problem, including microactivity, GRMHD, nuclear neutrino physics, equational state, neutrino photon transport, nucleosynthesis, et cetera, all the important aspects that enters into the physics that describe this problem. But we were aimed to really look at what happened more after mergers, not just the merger, but what happens at the post-merger once the central object merges into a black hole or a hypermassive neutron star or a stable neutron star, what happens to the nature of the remnant. In particular, looking at how the jet is launched, which is obviously the core that is responsible for the gamma ray burst. And the idea was to build a series of tools that would allow us to simulate the post-merger stage beyond 1 second. And obviously we know that we have to do this very accurately, because we have to resolve the scale of the MRI if we want to nail down the physics of the post-merger. Okay, so we therefore set ourselves this goal to build a series of integrated computational tools. And so I'm going to mention here a little bit what these are. So, and then I'm going to review briefly what we have done so far and point you to the talks, especially given by the younger generation of people around in our TCAN postdocs and students who have been really building all these tools for us, and now making us capable of addressing the first science questions, important science question in relation to the merger and the post-merger. In any case, so we started with this idea that we needed an initial data pipeline for both neutron star and obviously black hole neutron star mergers, and make this pipeline of data sets available for a variety of topological states in our ComPaBinary.org community site for the community for use it as we provide them. Then obviously our goal was to perform merger proper simulation, long-lived post-merger simulation for a variety of binary neutron star and black hole neutron star scenarios, with particular attention paid to both the gravitational radiation, but as well as MHD, calculating the prompt ejecta dynamics, orbiting bound matter dynamics and radial profile, jet launching and propagation to the ejecta, nuclear evolution in the ejecta and disk outflows, thermodynamics, nuclear evolution, photon spectrum, essentially everything. Well, that's a very ambitious goal, as everyone knows in this field. And so our strategy was to consider dividing the problem according to the physical characteristics. So using different codes for different regimes. And then we would develop a self-consistent handoff tools to transition from one code to another. So our view was really, we split the problem and we used the tools that are most appropriate for each of these particular problems and regimes, and then develop a translation dictionary among all these various tools and codes. Obviously, what we have to do, because as all of you who work in computational astrophysics, we are trying to include the most advanced physics in all these codes, but not all these codes have implemented things in a consistent manner. So what we have to work is to implement all of all of the physics, ranging from the tabulated EOS, neutrino physics, and other physics, MHD physics, in a level of consistency that would allow us stable data handoff from one code to another. And we're going to see we just achieved to do that. It's amazing, because there's a lot of details that goes into it, but we have been able to resolve these differences. I'm just listing some of those here: atmospheric treatment, ways you deal with the equational state, neutrino physics, treatment, MHD, and so on. And so now we have some of the post-merger simulation already underway at Tax Frontier. You're going to hear from the people in the team about this. Okay, so in our science goals, we had the idea that we would use these tools then to study various range of cases, those cases that leads directly into a black hole with a like accretion disk, but also other cases that would produce a disk orbiting an hypermassive neutron star that soon would collapse into a black hole. And then other cases here, like merger that last a few times longer and leave behind a heavy disk around a hypermassive neutron star. And then those cases that would produce instead a stable neutron star with a heavy disk, and also a black hole neutron star merger that produce a light disk. In reality, these are really very challenging, each of them very challenging cases. Obviously, this is a very ambitious goal, and we are at the moment working in simulations of the first few cases here. So this is still underway, we also, by the way, we're targeting opportunity based on the LIGO electromagnetic observations coming in, and where we know that we have still one of these serendipitous case that we are all interested, which I mentioned at the beginning, and well, everybody knows, I don't have to mention anymore. But so we are still looking forward to obviously hear from LIGO about observations, and LIGO and other electromagnetic astronomy observations, about future possible detections, and then go after them if we have the possibility once these tools are available. So we are proceeding by steps, and we start with magnetic fields that are in this range, for example, with realistic tabulated equation state, those that are available to us. I hope that we're going to hear a little bit more today of what, tomorrow, about what might become available in the future also in this arena. And then the idea was to perform these simulations for long enough, hopefully up to a second, but if not a second, half a second maybe, and then resolve them with enough resolution, to be able to get the physics. Okay, so I'm going to mention this now in the next slides, but here, and I apologize for the smallness of the fonts, but there is quite a bit of tools that we are developing, so it didn't fit all in one slide, and with larger fonts, but you see that. We have tools that we're working on, ranging from enhancing the Lorraine code, which is one of the most used initial data code for generating binary neutron star, black hole neutron star initial data, which is an open source set of tools. Then we're using two GRMHD Cartesian AMR grade code, Illinois GRMHD and Spritz. We have HARM3D, HARM3D actually plus NUC, which is a version of HARM3D, which include neutrino leakage and tabulated equational state. We're going to hear all about that from Ariadna and Morgan-Berthier. And the handoff toolkit, which is our way to actually transition from these Cartesian MR grids to spherical grids, because HARM3D is a spherical grid code. We do also, we have developed through separate funding from this network, a patchwork MHD code, and hopefully we're going to hear from Mark Cavara about how we applied this set of tools successfully already in the case of supermassive black hole merger, and we are in the process of incorporating this into the HARM3D environment for treating also the post-merger of binary neutron stars. And finally, we're going to hear also about this spherical NR code from Vasilios Mewis, which is again a spherical coordinate-based code, but it's built on top of the Einstein toolkit. Paramo, a particle acceleration code. Skynet is an open source code. We're going to hear from Yosef Zenati about how we use this code to post-process our simulations. And Pandurata and P-Trans-X, which is a novel Monte Carlo code for neutrino and radiation transport. And we're going to also hear about that on Friday. So what is coming next is actually a little bit of advertisement for the talks that are coming up after me about in the TCAN. So you're going to hear about everything about Lorraine, the enhanced public data repository Lorraine by Tamayi Gupta. So just here the visuals of the Hamiltonian constraint violation for one of the tabulated EOS that we are currently evolving. This is Elasta 20. She's going to tell us everything where we are in the production of this initial data, and that where you can get this data if you want from our public repository. Okay. So Leonardo Wernick is going to tell us what he had to work on together with Zach Etienne to enhance the Illinois GRMHD to include the equational, tabulated equational state, so to be able to read them successfully, as well as include the evolution of the entropy equation, electron fraction, and other important physics, including neutrino leakage, for example. And then other details, which actually these details are very important details that had to be incorporated into our codes to perform the handoff, the successful handoff to a post-merger code. Okay, so additionally, along the way, we actually we also brought in a new code. This new code is Spritz. It's been developed mostly in Europe as a follow-up code from the WISC MHD under the leadership of Bruno Giacomazzo. Lorenzo Enardi is a PhD student now starting here at RIT. And he's going to tell us a little bit about this new code. It's a new staggered A-field Cartesian MR code. And you're going to hear from him about all the advantages that we have using this modern technology, especially with staggered A-field type of codes. Okay, so and here is the one, I would say, the core of the really core about the development that we have been doing for this handoff that I'm mentioning, to transition from the Cartesian MR grid codes to spherical grids, which are more adapted to the geometry of the post-merger. So Federico Lopez Armengol, who is a postdoc at the TCAN, will here at RIT will tell us what it went into really completing this handoff tools. And so you see here some of the visuals. It's amazing. This, you can see just the neutron stars are really concentrated down here. You don't see them because this is the extent of the grid in spherical polar coordinates that you can achieve by doing this handoff to HARM 3D, now HARM 3D NUC. So you're going to hear about all of that, I believe, on Thursday. And we have our first post-merger simulation underway on Frontera for both the polytropic EOS and elastic anti-equational state. And this is our post-merger code. This is HARM 3D NUC now called. And Ariadna Marguerite-Berthier, she is going to tell us what she did to essentially enhance HARM 3D to take on tabulated equational state, and then being able to do neutrino transport. And she has a nice paper that with the collaboration that has been recently accepted in APJ. So you can go and check it out. This is the code that essentially will be able to carry on these simulations for accurately enough for very, very long time. So the code has been already tested in the case of a magnetized torus, and is currently being used for this handoff. Okay, so then our radiation transfer neutrino transfer is going to be presented by Jeremy Schnittman, I believe, on Friday. This is Pandurada PT Transax. And it has been mostly used it's a Monte Carlo code, and has been used to produce broadband X-ray spectrum from a single AGN and successfully so. And so you're going to hear a little bit about this, again on Friday. It's been successful in reproducing observational low hard and high soft state X-rays in binaries. And so we are now extending it to include also neutrinos. Okay, and by Joseph Zanatti, you will hear about the nucleosynthesis. He is gonna be telling you how we are using Skynet to do nucleosynthesis by post-processing our simulation data. Okay. And finally, this is a kind of the next generation codes. It wasn't it was not originally planned, but we inherited as we go. We actually pleasantly inherited additional tools. This is a particle acceleration tool written by our postdoc Jesus Reda Becerril, and it has the capability to essentially evolving energy distribution of particles and relativistic outflows. So we are planning to use it to estimate the light curves and spectra from the VNS post-merger jet. And multi-patch, this has been in the making now for several years, and it's been a major undertaking. Mark Avara is going to be telling everything about how we took the earlier developments in hydrodynamic by Shiokawa performed at Johns Hopkins and extended it to include MHD, but much more. So this new software infrastructure has been already applied in the context of supermassive black hole inspired simulations and has made our simulation 30 times more efficient than before. So you're gonna hear from Mark about this. Spherical NR, you're going to hear from Vasilios Mewes, who's now a staff at Oak Ridge National Labs and was a postdoc in our group. And spherical NR is built on the same principles using spherical coordinates for dealing with post-merger remnant. But it's built a little bit differently than HARM. It's first constructed on top of the Einstein toolkit, and is fully coupled to general activity. So that means that we can use this code, for example, to handle the hypermassive neutral star cases, where the space-time is still very dynamical. And the code is using higher order GRMHD, and it's a mixed finite difference finite volume code. So there's a lot of new things in this code, including a current limitation for ameliorating the filtering. So, you know, we have an issue with the current limitation if you use spherical coordinates, and there are techniques that have been developed to deal with that. So you're going to hear about that also on Thursday by Vasilios. And let's see, I think I'm reaching the end now. I don't want to take much more of the time because I think we have excellent talks today. And I just want to say stay tuned for the workshop, because there are really excellent speakers, and hopefully by the end of the workshop we have learned a lot. And yeah, enjoy the workshop, and thank you for listening.